I like had one or two computers, but it's wrong.
We'll spend the first half of class doing a little bit of trig review. Day one is going to be review. And then second half of class, we'll just continue to practice through the major topics of for next Tuesday's test. Monday, we'll do trig derivatives, first half of class. Then second half of class, we'll do continuous review. And we'll have a test review help session Monday morning and Tuesday morning. And then also Monday, fifth period and after school. So anytime you want to come in, do some review, I'm happy to do that. So, okay. So, what I want to make sure that we know from pre-calc is, well, from trig, it's just unit circle and being able to solve equations. Okay, we're not have to do as much of the detail that we did in pre-calc, where like sum and difference identity or verifying equations. You don't have to do all that. If you can solve equations and know your unit circle well, that will be that's really the most important thing for our trig unit. Okay, well, in terms of the foundation for our derivative trig unit. Okay, so let's do some review here. All of unit circle values are based off of these special right triangles, either 30, 60, 90 or 45, 45, 90 triangles. And the ratios are all kind of built off of these ratios, these values. Okay, I'm just going to first review the first quadrant of unit circle. The unit circle is where my radius from the center is going to be 1. Okay, and we just have to focus on finding order pairs. So we'll do quadrant 1 first, and then we'll build out the rest of the unit circle, and we'll do some examples of solving equations, and then we can revisit that on Monday. Okay. So unit circle values. Think of these as order pairs, and order pairs. You want to think of cosine as your x value and sine as your y value. Okay. The easiest order pairs are the ones that are directly on the axis. So this is 1 unit away. So my order pair is 1, 0. If I go up 1 unit, that's also 1 unit away. That is order pair 0, 1. So this is pi over 2 or 90 degrees. This is 0 degrees or 360 degrees, or you can say 0 or 2 pi. Okay. Okay, so these are really helpful because if I want to find cosine of 90 degrees, I can just look at the x value. I see a 0. Sine of pi over 2 is just equal to 1. Right. Cosine of 2 pi is the x value is just 1. Sine of 360 is just equal to 0. Right. We can just pick out either the x or y value. Cosine is the x, sine is the y. Okay. Pi over 3 is same thing as 60 degrees. Pi over 4 is 45 degrees. Pi over 6 is 30 degrees. Okay. All the rest of the unit circle are all kind of based off of these measures. Okay, let's talk about all the order pairs here. All the order pairs for unit circle on these special angles all have a denominator of 2. And I like to start at the upper left corner and just kind of snake my way through these points here. So I start with 1, 2, 3, and then I'm going to go back up the chain here. 1, 2, 3. You put square roots for all the numerators, just the numerator, but leave the 1 alone because square root of 1 is 1, so we can just drop that out. So Right, so these are very helpful because if I want to find cosine of 60 degrees, I can just go to my x value. Cosine of 60 is 1/2. Sine of pi over 4 is what? Yeah, √2/2. Cosine, or sorry, yeah, cosine of pi over 6 is √3/2, right? Okay. We can also find the reciprocals of these, right? Secant is just going to be the reciprocal of cosine. Cosecant is just going to be the reciprocal of sine. Another important one is tangent. Okay, so tangent of theta, in terms of sine and cosine, the tangent of theta is equal to what? That's sine over cosine. You can also think of it in terms of just y over x. So let's say I want to find tangent of pi over 3. You do y over x, but an easy way to do it without having to feel like I got to do a complex fraction here is cover up the 2's, because you know the 2's will just cancel out, and just do sine over cosine y over x, right? So tangent of pi over 3 is just √3/1, which is √3. Okay. Let me ask you this. What is the cotangent of 45 degrees? Yep, reciprocal of tangent, which is x over y, cosine over sine. So I know I'm looking at my order pair here for pi over 4. Cover up the 2's. Just look at the numerator. So x over y. So √2/√2 equals what? We're just doing review today. All right, so see if you can try number 1. Find all 6 trig functions, or find all the ratios of trig functions, 6 trig functions at 60 degrees. So use this partial unit circle to help you find everything that you need. You don't have to rationalize the denominator, but you can if you want. Okay. Any questions here? I would say you don't have to rationalize it, but the only time you may have to rationalize it is, let's say it was on there's multiple choice on the AP exam and your answer choice was rationalized, you just have to be able to get there. But if it's free response, you don't have to rationalize it. So once take it off for rationalizing or not rationalizing. Okay. Let's look at the full unit circle. I want to kind of do a quick review over the full unit circle. So let's go to 6A, page 6A. Right, let's go ahead and fill out the first quadrants real quick. and then we'll kind of walk through the rest of the quadrants. Okay, so first quadrant is filled in. Let me do the degree measures first. So there are angles that are related to that 30-degree angle. And these are the ones that are closest to the x-axis. Okay? So if the one close to the x-axis, they will all have a reference angle of 30 degrees. That just means we can always get to these angle measures. Let's do degrees first. Okay, we can always get these angle measures by subtracting or adding from the x-axis. Okay. So I know this is 30 degrees. So 30 degrees starting from 180. Oh, let me go ahead and fill out the this right here. So this is -1, 0. Okay, so 180 minus 30 will give me 150. 180 plus 30 will give me 210. And here, I don't want to do 0 minus 30, even though it's the same thing. I want to do 360 minus 30. So that's going to be 330. Right. All the angles in between are going to be 45 degrees away from the x-axis. So 180 minus 45. 180 plus 45, 225. 360 minus 45, 315. And then finally, the pi over 3, these are the angles furthest away from the x-axis. These are all 60-degree reference angle, 60 degrees away from the x-axis. So 180 minus 60 will be 120. 180 plus 60 is 240. 360 minus 60 is 300. There's a nice quadrant angle here. This is 3 pi over 2, 270, 0, negative. Just want to kind of throw at you just more relationships that you already know. Just want to kind of review these connections here. All the angles are how far apart from each other? 15 degrees, right? And that goes for all of them. So that's nice. You know that, they're all 15 degrees away from each other. That are clumped, each of the quadrants are all clumped together 15 degrees away from each other. All right, let's talk about the radian measures. Okay, sometimes I feel like sometimes the radian measures are the ones that kind of trip students up. But I kind of color coded it. Okay, so that means all the pi over 6 or 30 degrees, they will all have a denominator of 6. Okay, so closest to the x-axis, all denominator of 6. Okay, we'll worry about the numerator in a little bit. All the ones that are variations of pi over 4 will all have 4 in the denominator. And all the pi over 3, the 60-degree furthest away, I color coded using orange. All of that will have denominator of 3. Right. Just want to share with you some patterns in terms of the numerator, in terms of what goes in the numerator. You know, the numerator is going to be pi something, right? And let me just show you some nice numeric connections that you already may know. Second quadrant here, okay? The numerator are all going to have coefficients 1 less than the denominator. Okay, so 1 less than 3 is 2, so 2 pi 3. 1 less than 4 is 3, it's 3 pi over 4. 1 less than 6 is 5. So that's a nice connection there with those gradient measures. All right. Here, guess what that relationship is going to be? Numerator is going to be one higher. Yeah. So 1 more than 6 is 7. 1 more than 4 is 5. 1 more than 3 is 4. Fourth quadrant is a little bit not quite as easy, but it's just nice to just have a formula, or you want to memorize it. It's always going to be twice the denominator, but it's going to be an odd number, 1 less. Okay, so 3. So it's going to be times 2 must subtract 1. So 3 times 2 is 6. And 6 minus 1 is 5. So this kind of has that relationship as the second quadrant, right? It's going to be 1 less, but 1 less after you double it. Okay, 4 times 2 is 8. 8 minus 1 is 7. And 6 times 2 is 12. 12 minus 1 is 11. Okay. And all the order pairs are going to be the same. Okay, except the signs are different. But let's go ahead and fill out all the order pairs. All right, so 1/2 root 3 over 2, root 2 over 2, root 2 over 2, root 3 over 2, 1/2. And we'll talk about which ones are positive, which ones are negative. Okay, so anything in the first quadrant will have order pairs that are positive, right? If you think about any order pair in the first quadrant, everything is positive. If you pick a point in the second quadrant, what do you know about the x and y values? Negative x, positive y, right? So you can just adapt that for all the order pairs, put a negative for all the x values, and then keep the y positive. Imagine picking an order pair in the third quadrant. Order pairs will be what? Both negative, right? So I can take both my x values and y values and get the negatives. And then fourth quadrant is positive x, negative y. I put the key on the next page, 6b. So if I'm going too fast, you can always go back and forth until you practice spelling it in. Okay, I put another unit circle on 6c. There's a strategy called left-handed memorization method, but if you guys are comfortable with this, I would do this, but I can show you that method if you're feeling like you have some trouble memorizing or getting to these order pairs. Okay, one more thing I want to do before we go to our test review is I want to make sure that we know. Oh, sorry. Okay, page 8c. want to highlight the things that we should know. We should know all the relationship between sine, between all the trig functions and the reciprocal relationships, right? Sine and cosecant are reciprocals. Cosine and secant are reciprocal. Tangent and cotangent are reciprocals. Tangent is sine over cosine. Cotangent is cosine over sine. Okay. Pythagorean identities as well. Okay, that's an important one. Sine squared plus cosine squared equals 1. But there's two other ones that we can derive from the Pythagorean for this first one. And that's just simply by dividing by everything sine squared or everything cosine squared. Okay, so there's no need to memorize the second and third one. You just divide by either cosine or sine to arrive at all your identities. Double angle, these are also good to know here as well. Sine 2 theta is 2 sine theta cosine theta. Cosine 2 theta, there's 3 variations. If you know one variation, and you can always make substitutions to get them in terms of either all cosine or all sine. So if you just know one of them, you can get to the other ones. So I just focus on knowing this one. Even and odd functions, it's good to know sine is an odd function, cosine is an even function. This is, I think, the other stuff here, the cofunctions, not that important. We're not going to have to worry about that too much. Unit circle values, definitely know those. And then the graphing is not that important as well in terms of transformations. So we cross those out as well. Okay, but it's important that we know how to solve trig equations. We'll do some more on Monday, but I want to at least get through one before we move on to our test review. So page 1, bottom of the page. We don't have to worry about finding period, amplitude, and all that, but first page, being able to solve an equation, that's important. Okay, I want to make sure that we can do it as well. Sine of 2x equals sine x. I want to find all the x values between 0 and 2 pi. So first thing is, well, it looks like I can expand on that double angle identity. So sine of 2x can be expanded into 2 sine x cosine x. All right, I want to find all the solutions here, but I don't ever want to do this. I don't want to divide both sides by sine. Okay, yes, algebraically that's not incorrect, but if you're divide by a variable, you're losing solutions. So we don't want to ever divide by a variable, especially if we're looking for solutions. Rather, we want to bring everything over to one side, subtract that sine x over, and set equal to 0. Okay, what do you see here? What can we do here? Right. I can factor, right? GCF, factor out sine x. Now, when you factor, you're basically dividing that GCF away from the rest of the expression. Okay. So if I take that 2 sine x cosine x, if I divide the sine x, what's left? The cosine x that goes inside the parentheses. If I take this sine x and divide by sine x, what's sine divided by sine? 1, yeah, minus 1. Got factor form, set equal to 0. These are really 2 equations that we can solve separately. And we're going to need unit circle values to help us get to our x. Okay, so sine of x equals 0. Let's think about this. Sine of what measure? Okay, we're dealing with radians here. Sine of what measure is going to be 0? Sine of 90 is going to be 1, right? It's going to be sine of 0 or 2 pi, but 2 pi is outside my range, so it's just going to be 0. Okay, so sine of 0 degrees or 0 radian measure is equal to 0. All right, that's one solution. The other solution, let's try to get cosine by itself. Where is cosine equal to 1/2? Okay, power of 3. And there's another quadrant where cosine is positive. First and fourth, okay? And the fourth quadrant variation of pi over 3 is pi over 3. All right, multiply by 2, subtract 1. Okay, so we have 3 solutions. I also have this this acronym to kind of help us, or it helps me remember the signs of my trig values. So first quadrant, A means all. All my trig functions are positive in the first quadrant. Second quadrant, only sine in this reciprocal are positive. So second quadrant, only sine and cosecant are positive. Everything else is negative in the second quadrant. Third quadrant, only tangent is positive. Okay, tangent and cotangent are positive. Okay, sine, cosecant, secant, cosine, everything else is negative in the third quadrant. In the fourth quadrant, only cosine is positive. So cosine and secant are positive. Okay, the other 4 trig functions are all negative. Okay. All right, just want to make sure that we can do some trig review, but we can move back to our test review, and let's do some problems there. Okay, if you guys can go to page 19, I want us to do another okay, let's go back to page 19 in your packet. I think we've done something similar like this, but I wanted to kind of get that additional practice. This is a curve sketching problem, but I'm not going to ask you to sketch the graph. I just want you guys to go through that process of being able to create your derivative sine line, f prime sine line, test each interval, and then also determine relative max, relative min, increase, decrease, and then the same set of information with the second derivative sine line. Okay. So x over ln of x, we start off by finding the derivative. To find the derivative, we have to go through what? Numerator, denominator, we got to go through quotient rule. Okay, so let's set that up. Go through quotient rule. F prime g minus f g prime all over g squared. Key's on the next page, but see how much you can do without looking at the key, and I'll follow up with steps. Okay, f prime g minus f g prime. Do all over denominator squared, right? All over natural log of x quantity squared. Careful, we can't bring this 2 down in front, okay? This is not a log property. That 2 is not just with the x, the 2 is with the entire natural log function, so that 2 has to stay. But we can do a little bit of cleanup, right? Numerator can be cleaned up to be what? Natural log of x minus 1, all over natural log of x squared. Okay. All right, next up, I want to find critical points. So critical points can come from both the numerator and denominator, right? So we're going to set both equal to 0, because even if a value is undefined, we still want that to live on the slope sine line, because we want to separate our intervals of increase decrease, right? And I highly encourage you guys to memorize the natural log graph. Just being able to have that natural log graph with the asymptote, the 2 order pairs, and the sketch of the graph, you can ballpark so many important values without the use of a calculator, okay? Without the need of a calculator. All right, so let's talk about the first one here. Natural log of x minus 1 equal to 0. Natural log x is equal to 1. Natural log of what value is equal to 1? E. Okay, so the graph is helpful, but you can also work your way through algebraically by solving for x by involving e. You know, e raised to the natural log. E and natural log are inverses. E and natural log cancels out. The x drops down. X equals e. We get the same answer algebraically. Okay. Second thing, natural log of x quantity squared is equal to 0. Take the square root of both sides. Okay. Natural log of what value is equal to 0? 1. Okay, so the graph is helpful, but second option, you can algebraically get to your answer as well. Raise both sides. E is the base. E natural log goes away. X equals e to the 0. Anything to the 0 power is 1. So we have our 2 critical points. Now, if you look at your original function, okay, your original function has natural log in it, so that is automatically going to give it a restriction. And there's no negative number that x can handle because of natural log. So we know our slope sine line will just begin at 0 and then move to the right. No negative numbers. Okay, I'm going to place my critical points. And I'm going to test numbers against my derivative function, right? So let's pick some values here. Between 0 and 1, I can choose 1/2. Between 1 and e, I can choose 2. Between to the right of e, I can choose e squared. I like that. Or 3. 3 is fine as well. Both are good. E squared feels a little bit cleaner, but 3, you can get everything that you need from the graph as well. So let's go through each of these. We're going to test these against the derivative function, and we just care about whether it's positive or negative. Okay. All right. We needed to be able to ballpark some values here. So natural log of 1/2. Okay, 1/2 is for x. Natural log of 1/2. Okay. Look at your graph here. Natural log of 1/2 is what? Negative. So somewhere here it's like negative 0.6. But if you just know that's negative, that's good enough. A negative minus 1 will still be negative. Denominator is being squared, so denominator is always positive. Negative over positive is negative. So I know my graph is decreasing. Okay, let's plug 2 in. Natural log of 2. Okay, look at your graph. Natural log of 2. Where's natural log of 2? What y value is that? Around 0.5, right? It's definitely less than 1, but greater than 0. So let's say 1/2. So natural log of 2 is, let's say 1/2. 1/2 minus 1 is negative. Over anything squared is positive. Negative or positive is negative. All right, e squared in for my numerator. Okay, natural log of e squared minus 1. This is nice because I can push this 2 down in front. Right? What's 2 natural log of e? Well, natural log of e will turn into just what? Just 1, and 2 minus 1 is 1. So positive over a positive is going to be positive. But it'll also work with 3, right? Using the graph, 3 is fine as well. Natural log of 3. natural log of 3, I know is to the right of e, somewhere here. That's going to be a decimal value of what? 1.1, 1.2-ish, right? 1.1 minus 1 is positive. Positive or positive is positive. Okay. So that graph alone can just help us find so many useful ballpark values without having to feel like we're stuck not knowing what that is without a calculator. Okay, so what can we say there? We have 2 intervals of decreasing, 1 interval of increasing, and we don't care about these values anymore, right? These do not play a role. As soon as we get the signs above, we don't want to include them in any statements. So on the test, if I asked you for interval of decrease, you would say from 0 to 1 and from 1 to e because f prime is less than 0. Increase would be from e to infinity because f prime is greater than 0. You guys demonstrated that you were able to write all your because statements very well on the test. So if I asked you for that again on this test, you guys should be fine. Okay, is there a relative extrema? Yes, there is a relative what? Relative min. If I asked you for the order pair, you would take that e value and to the original, right? To the original. So e over natural log of e. Natural log of e is 1. E over 1 is just e. Relative min because f prime changes from negative to positive. All right, so starting at y prime, we can go one derivative down to get to second derivative. And if I want to get to the second derivative, what we have to involve here? Quotient and chain. Okay, let's go through that. Quotient and chain. Start with quotient. Okay, f prime. Function. Back to f. Okay, g prime, this is where we have to use what? Chain rule. Yep, outside, inside. Okay, outside's derivative. 2 parentheses to the first power. Inside's derivative, natural log of x becomes 1 over x. All over denominator square. Natural log of x is already square, so I got to square that again. So eventually become to the 4th. Okay, it looks like a mess, but we can find our critical points by doing a little bit of factoring in the numerator. So what I mean by that is think of these as 2 separate terms, okay? 2 separate terms with the subtraction sign in between. So I marked that with green there. So I got that first expression and the second expression. And I want us to, and if we move this through faster, if we don't have to worry about expanding everything out, but instead of taking out a GCF, that will kind of speed up the process of condensing and simplifying our expression. So look at those 2 expressions. What is shared? What's common? What can we take out of both? Yep, 1 over x and natural log of x. So that's going to help clean up our problem a lot faster. So I'm going to divide 1 over x natural log of x from both expressions. So if I were to divide 1 over x natural log of x out of the first expression, what's left over? just 1 natural log of x. Okay, so from the second expression here, if I were to divide out the 1 over x and natural log of x, what remains? Yeah, 2 and this natural log of x minus 1, right? All over natural log of x quantity to the right. All right, so now that the GCF is out, it's free to look below to see if there's anything that's common that we can reduce. Natural log of x can go away. There's 4 below. I can take 1 from both, and I'm just left with 3. Do a little bit of cleanup here, right? I can distribute the negative through. There can be some light terms that we can deal with here. All right, let's see what that cleans up to be here. I have 1 over x sitting out in front. Natural log of x minus 2 natural log of x, what does that become? Negative 1 natural log of x, right? Over natural log of x quantity cubed. All right, I'm going to rearrange it, but essentially I can just push it into one fraction, and that's relatively clean. Second derivative that we can look for critical values, right? All right, where do we look for critical points? Numerator and denominator, okay. All right, so three things I can look for. The 2 minus natural log of x equal to 0, the x equal to 0, the natural log of x cubed equal to 0. Okay, first one here, 2 equals natural log of x. Now this, we're not going to be able to look at the graph to figure out because it's not an easy one to find, but we practiced going through algebraically, so we should be able to get to our x value here, raise both sides, e as the base. E natural log goes away, I'm left with x equals what? E squared. Okay, so that's one critical point. X equals 0, that's already found for us. We can stop there. Natural log of x cubed equals 0. Take the cube root of both sides. I'm left with natural log of x equal to 0. X equals what? 1. Yeah, raise both sides. Or we can look at the graph. All right, so here's my second derivative sign line. Again, we're starting at 0 and moving to the right. 1. Let's choose some convenient values in between to test. 1/2. Okay, what can we take advantage of between 1 and e squared? E, yeah. 2 works as well, but we like e. And then to the right of e squared, e cubed, right? So it's going to be very easy and clean with natural log involved here. So again, we're going to insert into this, second derivative function here. Test out the signs here. Okay, so 1/2 in for natural log of in for x. Natural log of 1/2 is around negative 1/2, negative 0.5. 2 minus the negative 0.5 is positive. Okay, so numerator is positive. Denominator, I get 1/2 times natural log of 1/2 cubed. That natural log of 1/2 is negative 0.5. Negative 0.5 cubed is still negative. So positive over negative is negative. Second derivative here, so not decreasing slope, but this is going to be concave down. All right, let's test out e here. Natural log of e is 1. 2 minus 1 is positive, right? Bottom here, e times natural log of e cubed. Everything is positive below here as well. Positive over positive, positive. Okay, e cubed, I'm going to work this out. Maybe there's more things going on here. Okay, what can I do to clean this up here? Bring the 3 down, okay. So natural log of e is 1, 2 minus 3 is negative, and the denominator is all what? It's all positive, so negative or positive is negative. Okay. If I want to say intervals of concave down or concave up, we can just look at our sign line, but again, don't use these numbers anymore. These are not going to play a role at all in your interval. Okay, interval concave down, you'll be able to say the first and the third interval here. Careful, if I ask for a point of inflection, how many points of inflection do you see? It looks like 2 because there's a change in concavity, but there's something off about 1. One is the what? Natural log of 1 is 0. Can I have 0 in the denominator? Okay, so that is a vertical asymptote. Okay, it doesn't exist. There's concavity change, but if there's an asymptote, we can't call that point of inflection. There's only one point of inflection, okay, at e squared. If I want to find the y value, back to the what? The original. Yeah. So plug e squared into the function, I get e squared over natural log of e squared. Natural log of e goes away, 2 drops down, e squared over 2 is the y value of my point of inflection, and the reasoning is because f double prime changes signs. Okay, hopefully you guys can spend some time over the weekend, continue to practice these problems. I extended the test date all the way to Tuesday, so take advantage of these extra days. Okay. Come up and get your phones. I will have a test review, morning review, Monday and Tuesday morning, and Monday afternoon, and Monday during 5th period. So I'll send out a reminder this weekend. I knew once I got to E and E cubed, I was safe. The natural log of E is positive, E is positive, so everything here is safe. For 1/2, I had to take some time. 1/2 is safe. Natural log of 1/2 is negative. Negative cubed is still a negative, so it's gonna be negative. Okay, but 2 minus natural log of 1/2, natural log of 1/2 is negative. 2 minus a negative is positive. The positive or negative is negative.
Now we're gonna do a couple of Thursdays.
Yes, eventually. Monday or
You gonna be.
Monday, if I get back to Monday.
Bro, like, it doesn't matter, but I hope we're inside, yeah, because I be getting my thought.
Abigail, you get in?
Like, I was thinking, I need a straight haircut, but it will. I had to go, I didn't train them, I took like 30 minutes, like, yeah, think of it, You think I'm staying here all day? He helped me train the brain. He was wanting to do something wrong. He was on this team like this. You can get training people, next people got hurt on the. He can. He's just supposed to hand on like stuff used with the gun. It's just like, it's like a weight. It's like fed hot ice and.
Can I go get my water bottle?
He just doesn't make sure my ankles, my toes. Where's toes? I'm like, we're 3 times to have known about it.
I think it was like.
I haven't asked him.
But like, it's hard to get a hold
In a place. Like 2 years ago. And it got close to the building. It's not moving yet. Like, still. It's like, one of the dudes at King's Ridge, I think he's right, for like the bonus stories. He like, tore his ACL. And he was. Like.
I got the last one. The last one was perfect.
They probably forgot my password. Thank you, Mr. Yates.
Did you get a chance to see, oh, sorry. Okay, you want to see her, just try to find her today. This last day after the fee. Okay, thanks.
Okay.
We're moving on to the-
That'd be so funny.
Got this already, or?
Yeah.
Okay.
Oh.